So this lesson is dealing about the parallel plates, and the very first topic that we will treat is the potential difference between the two parallel plates. But before we move to the difference between the two potential difference between the two parallel plates, let's clear what are the parallel plates. So if we have two plates, so let's suppose plate A and plate B, that are parallel to each other and they have a difference on potential, like a different potential energy. But plate A has a different value of voltage and than plate B. Then between those two plates exists a difference on potential energy. Now the plate that has higher voltage, it's considered to be the positive plate. So if we have the positive sign on plate A, let's say, then that means that plate B has a lower voltage than plate A, and it's considered to be negative. When we are when we are connecting it with a power source, then the way that we represent it is with those two lines, so that one is a higher one or longer one than the other, and that means that this is connecting, or this is giving plate that is connected to a higher voltage than the other plate. When we are saying that the difference between the two parallel plates, voltage between two parallel plates is, let's say, 10 volts, that means that the relative difference between A and B is 10 volts. So A may be 20 volts, therefore B is 10 volts, but A may be 50 volts, therefore B is 40 volts. So the difference between the two plates, the relative difference between the two plates, will give us the potential difference between two parallel plates. Now, let's see a bit more in terms of the parallel plates. So let's suppose that we have two plates that have a difference of potential energy of plate A and plate B. The difference of potential energy of 100 volts. 100 volts. That means that if this is 0 volts, then plate A, being a positive one, saying that it is a positive one, will have a voltage of 100. This is, let's say, negative 20 volts. Then plate B will have a positive 80 volts, and so on and so forth. So that being positive 10 volts, that means that the voltage of plate BA is 110 volts. Now, when we place a charge between the two plates, then we see an interaction, meaning that the charge will move in one direction or the other. So let's suppose that we have plate A and plate B here, and this is negative and this is positive. And now what do? Is we place a negative charge here. So we know that the negative is attracted to positive, so the negative charge will fall to the positive plate. But if we place on the plate B, we place a positive charge here, then what will happen is that this will fall into the negative plate. Now, since the charge is moving when we are placing it between the two parallel plates, then naturally we think that there is an electric field strength that exists between the two parallel plates. So now let's suppose that this is negative plate and this is positive plate. So now what do we do in order to identify the electric field strength, which, by the way, we have said is a vector that has magnitude and direction. And we identify the magnitude, the direction, using the test charge. So now again, what we will do is we will place a test charge here, which the condition for the test charge is to be a positive charge, and it is very small in comparison to the charge of the to the source. So now if we place positive charge here, where is this positive charge naturally going? To plate A or to plate B? A, that is negative or lower voltage, or plate B. So I hope that you all said that it's going toward plate A. And now again, we place the charge somewhere in here. And again, the test charge will go toward plate A. So therefore, we can say that when we have two parallel plates, positive, negative, or negative, positive, and then the electric field strength direction is toward the negative. So electric field is this way. Or this way. It's, as you see here from the field configuration of the electric field configuration between the two parallel plates, the field lines are equal distance between each other, which tells us that the electric field strength between the two parallel plates is uniform, meaning that in any point, at any point between the two parallel plates, the magnitude of the electric field strength is the same. This is very similar to the gravitational field strength near the surface of the Earth. So when we have a field strength near the surface of the Earth, then we have the constant value that is 9.81 meters per second squared, which we assume that is uniform at a surface or at a height near the surface of the Earth. So now let's suppose that you have two parallel plates, so that this is positive and this is negative, and for simplicity we will say that the change of voltage between the two is 100 volts, and then the distance between the two parallel plates is 10 millimeters. Okay, so what does that means is that if we have a point A that is at the negative plate and a point B that is at the positive plate, the change of voltage between those two being the 100, the electric field strength will be the same because it is uniform. And when we are at a distance that is, let's suppose, 5 millimeters away from plate A, which is the mid distance. So when we have a distance here, 5 millimeters, then the voltage between, the change of voltage between plate A and the mid distance is equals to 50 volts. And when we have a distance that is, let's say, 7.5, millimeters, then the change of voltage is 75 volts. And when we have a distance that is, let's suppose, 2.5, millimeters, then the change of voltage in this case is 25 volts. And when you are at point B, that is 10 millimeters away, then the change of voltage will be 100 volts. This tells us that when you are in those lines that are the same distance from the plates, when you are on those lines, the change of voltage between a point C and a point D, delta V between C and D, is equal to 0. There is no change of voltage between C and D or any point, E and F. The change of voltage between E and F is equal to 0. So now if we suppose that we have two parallel plates that have a difference of voltage between each other. Let's suppose that this is positive and this is negative. The electric field strength between the two will be in this direction, while the lines that have the same voltage, which are known as the equipotential lines, are parallel to the parallel plates. So those lines here are known as the equipotential lines, meaning that the difference of voltage between any point on those lines is equal to 0. So now if we go back to what we said to the first part of the electric potential energy, we said that the electric potential energy is delta V times Q. Okay, so on the other hand, based on the work and energy principle, this is equal to the work done on the charge, or the work done by charge. This tells us that when we have a charge Q, that starts at the starting point here and goes around between the two parallel plates, but ends at the same equipotential line end point here, then the work done on the charge or done by the charge is equal to 0, because the change between the starting point and the end point of the potential difference is equal to 0. So it is independent of the path that the charge is doing, as long as it is ending up at the same equipotential line, which is a line that is parallel to the plates. Okay. Now, how can we calculate the electric field strength between the two parallel plates? So electric field strength is a vector quantity, meaning that it has magnitude and direction. We said that now we are entering into a zone where we calculate direction in one way and magnitude in another way, in another form. Okay, so now the direction of the electric field strength is defined using the test charge. we said that the electric field strength, when it is a point charge, then it has the electric field strength is calculated. So point, we dealt with that, is calculated with Q of the source over R squared, where R is the distance between the center of the source and the point that you are measuring it. And when we have parallel plates, it is calculated as delta V over delta D, where delta V is the change of the voltage and delta D is the distance of the distance between the two plates in meters. So now when we had the point source, the electric field strength was non-uniform. It's changing as you were moving away from the source. And when you have parallel plates, the electric field strength is uniform. The units that we used for the electric field strength when we were calculating it was newtons per coulombs. And then we know what newtons are, kilograms meters per second squared over coulombs. And when we have the parallel plates, the formula that we use is delta V over delta D, which is volts per meter. Those two are the same. So even if you do the calculations, those two will be the same units. But just keep in mind that when you have a point source, the electric field direction still is defined by using the test charge, which is always a positive and way smaller than the source. And when we have a point, it is not uniform. When we have parallel plates, is uniform. That means that at any point between the two parallel plates, at any point between two parallel plates, point 1, point 2, point 3, point 4, point 5, at any point, E1 is equal to E2 equals to E3 to E5 equals to any point equals to delta V over delta D. Okay. Now let's see how can we calculate and define the electric field strength between the 2 points, two parallel plates. Let's suppose that we have 2 plates that are connected, are powered by a battery that looks like this. Okay, and the change of voltage between the battery is, let's say, 30 volts. And we have a difference of, or the distance between the 2 plates is 2.50 times 10 to the power of -3 meters. So what we are doing is we are finding the electric field strength between those 2 parallel plates. First of all, when we see a diagram like this, the power source has 2 lines, a short and a long line. That long line means that the plate that it is connected with, this line, it's considered to be with a higher voltage. And the short line means that the plate that it is connected with is with the lowest voltage. So now, in your mind, what you have to do is, if you don't remember, the electric field strength between the two parallel plates goes always to the lowest voltage. You have to place a test charge here in between, and then say, which is always positive and very small in comparison to the source, and then say, where is this charge naturally going? And now we know that the positive is attracted to negative, so the electric field will be toward the negative. So the direction is down. Now let's calculate the magnitude, which, since we are dealing with plates, will be delta V over delta D. And this will be 30 volts over 2.50 times 10 to the power of negative 3 meters. So the magnitude of the electric field will be 30 divided by 2.50 times 10 to the power of negative 3. 30 divided by 2.50. It is 1200 volts per meters, or you can say 1.20 times 10 to the power of 123 volts per meter. This means that at any point between those two plates, what do you see is an electric field strength of 1.20 times 10 to the power of 3 volts per meter. I hope that this makes sense. Now what we will see for the second part will be when we have a charge that is moving between the two parallel plates, what is happening. But this is becoming a bit long, so I will stop here and then you will see the second part of the lesson.